Welcome to the eighth and final module in our series on constrained optimization. This discusses an economic interpretation of duality and shadow pricing. We've seen over the last 7 modules that duality as applied to optimization is a pretty complex topic. And one way that we can compare the primal and dual optimization problems as well as the solutions that they yield employs an economic interpretation. In that interpretation, we can imagine the primal problem as a resource allocation problem. How can we optimally allocate resources to generate the most beneficial output? If we look back at the example from the previous module, the primal formulation was asking us to determine how we can use energy and manpower optimally in order to generate some mix of product X1 and product X2. The dual problem may be visualized as a resource valuation problem. How to optimally determine the value, or shadow price, of those resources to generate the most beneficial output. Now, this comparison still applies to problems with no obvious monetary or economic component, but fortunately the example that we presented in module number 7 has a pretty obvious economic component, which will make this conversation a little bit easier. So we're going to use the previous module's factory example to frame this economic interpretation. And as for most linear programming problems, which the example from module 7 was a linear programming problem, we assume strong duality, right? The primal and dual formulations are feasible, etc. And so the equality of the primal and dual solutions as dictated by strong duality facilitates a more clear discussion. If strong duality doesn't apply, then mu represents an approximation or a limit on the true market prices, and that just makes this conversation way more complex than is appropriate for the purposes of this module. Now, for this example, we have two parties, factory K and factory M. The dual problem assumes that factory K agrees to purchase all available resources as dictated by B sub H from factory M at the unit price mu. So we have factory M with resources, and it sells those resources to factory K, who then processes them and essentially generates those products X1 and X2 that we talked about in the previous example. Array C defines the minimum unit price at which the product will be sold, and factory K can potentially sell the product at a slightly higher price than factory M. Don't want to talk about this too much yet, but we do have to leave the door open that factory M can also produce this product, but we're going to assume that factory K, because they're quote-unquote better at it, can sell it at a slightly higher price. That's not a hard assumption, but it does help with the intuition of this problem. So here's a figure that visualizes the problem. We have factory M. Again, I know there's some restatement here. Factory M sells resources X to factory K, and we're assuming that all the resources X will be sold at the equilibrium price mu and bought by factory K. Factory K buys those resources X, processes those resources, and sells a product Y. We assume that all the product Y will be sold at the minimum unit price or greater than the minimum unit price. Now, this additional arrow up here is simply saying that factory M does have the option of processing the resources themselves and selling the product Y directly. So primal optimization is performed from factory K's point of view primarily, while the dual optimization is performed from factory M's point of view. These point of view designations are subject to interpretation. However, they do facilitate this discussion, but we'll see at the end that really the dual optimization generates a solution that is optimal for both factory K and factory M. Factory M wants to maximize the income from their resource sales, that should be X. And this requires factory M to determine the optimal market price for scarce resources. We'll come back to this term, why we're designating scarce resources. We call these market equilibrium prices the shadow price. As stated above, this contrasts the primal optimization problem that's performed predominantly, again, this is still subjective, right, is performed primarily from factory K's point of view, where factory K wants to maximize the income from product sales. Shadow prices represent the gradient of income to the number or the units of resources purchased. So we see here we have mu is equal to the estimated delta F, or change in the income generated from selling those products, with respect to the number, or we could say the delta, of the number of units of resources purchased. It essentially tells us how sensitive the income is to changes in the number of units of resources purchased. And obviously, right, if we purchase more resources, we can generate more product, which then leads to increased income. So here we have a slide taken directly from the previous module. It demonstrates how we took, for our factory example, how we took our primal optimization problem and converted it to its dual form. I'm not going to go through this in detail. If you need a refresher on that, I recommend you go back to module number 7. What I really want to focus on is interpreting these expressions and trying to extract a more intuitive meaning from them. So let's start off with the primal side of things, the primal optimization problem. This is easier to comprehend, I think. We know that the primal problem asks us to maximize the income generated by factory number K, which is equal to the unit price of the products times the number of units that we sell. Makes sense. It's subject to the constraint that the amount of resources that we use should be less than or equal to the total availability of those resources. Now let's move over to the dual formulation. This objective function, I think, is a little bit less intuitive to understand. The objective function for the dual problem is the dual Lagrangian, and that's equal to B sub h times mu. This same B sub h, and now our shadow price is represented by mu. B sub h, as we've said previously, represents the number of units of resource X, or resources contained within X, that are purchased, and we multiply that by the shadow price that we already said represents the change in income from selling those products per unit of resource X, or unit of each resource within X purchased. If we apply some algebra here, we can see that these two cancel out, and the result is that the dual Lagrangian is approximately equal to f of x, the income generated by factory K. Now, for strong duality, we can replace the inequality with an equality and assume that the minimum of the dual Lagrangian function is equal to the maximum of the primal objective function, again, assuming we're adhering to all of our constraints. So now we are going to dive into this red equation in more detail in coming slides, but I'm just trying to frame that discussion. Now let's take a look at the constraints for the dual problem, represented in blue. What we see is that it's equal to, or is defined as AH transpose, this same AH, times the shadow prices must be greater than or equal to C. What does that mean? So A sub H represents the units of resource X purchased, or sold and purchased, per unit of product Y generated and sold. Essentially, how much resource is needed per unit of product Y generated or sold. We multiply that by the shadow price, which we've already talked about several times, and that represents how the income from selling products changes per unit of X that we purchase. And so, again, we can apply some algebra here, and what we see is that these two, the product of these two terms, gives us the total cost of the resources required to generate 1 unit of product Y. Okay? Now, that must be greater than or equal to the income to factory K per unit of product Y generated or sold. Right? This is the same C that we had in our primal objective function up here. That's C. And so this is the minimum income generated per unit of product Y sold. Now, this brings up some questions, okay? 2 questions specifically. First, has to do with our dual objective. The dual objective is to minimize the benefit, where the dual Lagrange function is equal to F, the income generated by factory K. We want to minimize that as well as the shadow prices, but why? That kind of seems counterintuitive. Wouldn't we want to maximize the income? And then the second is we see that the estimated total cost of resource X required to generate 1 unit of product Y must be, or is constrained to be, greater than the minimum income generated per unit of product Y sold. Why is that? Again, counterintuitive. It doesn't make any sense that this business could succeed if the resources required to generate a product are more expensive than the price at which we can sell it. Now, I'll give you a clue with regard to the answer to this question, and that lies in the use of the term minimum here. So we're going to address both of those questions. I'm actually going to start off with the second one at the bottom. Again, why is the total cost of resources required to build a unit of the product, why is that constrained to be equal or greater than or equal to its unit price? It doesn't really seem intuitive. So to answer that, we need to ask a couple of questions. And first is, what is the feasible region for the dual solution mu? We kind of already said this, but again, it assumes that any feasible cost of resources, which is equal to A sub h times mu, required to generate a single unit of product must be greater than or equal to, again, key here, the minimum price C at which it's sold. We already understand that. Now we get to the interesting question. But if that's the case, how is Factory K going to profit? A couple things. First, the dual optimization is performed, again, I'll write here subjectively. Very messy writing, sorry. It's performed subjectively from Factory M's point of view, not K's. So this dual optimization is focused on how much money M is making, not K. More practically, we assume that Factory K can sell the product at a slightly higher price than the minimum that Factory M is considering in its dual optimization, and in that way, Factory K can generate some profit. So, what happens if this constraint is violated? Right? The constraint says that A sub H times mu must be greater than or equal to C. So what if that's less than? So if we violate that constraint, then what we see is Factory M won't be motivated to sell its resources, right? Factory M will be motivated to produce the output and sell that at the higher price C. Now, I know practically that doesn't make sense. Factory M would have to develop a whole new infrastructure to generate the products. This is a basic interpretation of a basic example. So we're not considering costs, overhead like that. We don't consider, like I just said, overhead, the cost of building the factory, or the fact that, according to this example, we're saying that Factory M is selling manpower to Factory K. Again, we're going to have to gloss over a lot of those details in order to make this interpretation, this broad interpretation and discussion work. So we answered the second question in blue. Now let's go back to the first question. And the dual objective is to minimize the benefit and shadow prices. Why? Doesn't it make sense that they will want to maximize the income? So let's compare the objective functions. The primal objective function f calculates the income generated by Factory K as a product of the number of units sold and the unit price of the products. The dual objective function calculates the income generated by Factory M as a product of the amounts or number of resources sold, as denoted by B sub H, and the shadow price of those resources. I don't think we need to go over this expression again. Really what we see is we can use algebra to cross these two out, right? The product of the number of units of resource X purchased times the shadow price of those resources, assuming strong duality, yields our f of x, or an accurate and equivalent approximation of f of x. But now let's ask the more interesting question, is why is this the case? Factory M wants to minimize the dual Lagrangian as well as the shadow prices. Why? Remember, they don't want to minimize the shadow prices. The shadow prices are equivalent to the unit price at which the scarce resources are sold, and Factory M does want to sell the resources at the maximum reasonable price. But, and we can replace this because we've been largely using the term feasible instead of reasonable. But what is reasonable? What is feasible? The market determines that. Factory M must use minimization to determine the market equilibrium price or shadow price of all scarce resources. If Factory M refuses to sell their resources at the market equilibrium and sells them at a higher price, then Factory K won't purchase these resources. They won't be motivated to purchase the resources. And as such, Factory M has no choice but to apply minimization, which is required to participate in this market of selling resources for generating products. So I think we've answered those two questions relatively well. Now let's try to interpret the meaning of the shadow price in a more robust manner. So we keep talking about scarce resources. Okay, the shadow prices for all non-scarce resources are effectively zero. For scarce resources, the shadow price is non-zero, whereas for non-scarce resources, the shadow price is zero. A non-scarce resource is one whose constraint is inactive or non-binding. Right? This should sound familiar. We talked about this a lot in the past, especially when we were discussing the KKT conditions. Now, this does not necessarily mean that any resource that's not scarce has no market value, right? You could still buy it as a reserve for the future. It means that for those non-scarce resources, the shadow price would not necessarily be equal to the market price. And this, again, is a side effect of the fact that we're looking at a pretty simple example, a pretty basic example. So, Factory K, the customer for Factory M, is motivated to pay the shadow price mu for 1 unit of an additional resource X because they are likely, in fact they're guaranteed, to generate at least the equal income. Or perhaps more, because we've already said that Factory K can can sell them at a slightly higher price potentially. Now this example does not consider processing overhead or the fact that Factory K obviously has to spend some money in addition to that spent on buying resources in order to generate a product. So let's take a look now at some non-feasible and suboptimal solution examples, because I think this also will help us understand why the dual problem is formulated the way that it is. So the first one we're going to look at is what happens if the dual constraint is violated. Normally, AH, mu, must be greater than or equal to C, but what if it's less than C? What if the cost to produce a single unit of the product is less than the price at which it may be sold, while we're assuming that we've optimized, right? We've minimized our dual Lagrange function. So in this case, Factory M is not motivated to sell resources at a price lower than the minimum guaranteed for its final product. The shadow prices are too low. And as we've said before, a little bit of repetition here, Factory M is motivated to process those resources and sell the products. We're ignoring all the additional overhead and costs that would be associated with that. The second infeasible or suboptimal solution would be one where the constraints are adhered to, right? The total cost to generate one unit of the product is greater than the minimum cost at which it may be sold, but we haven't minimized our dual Lagrange function fully. All right. And so in that case, the shadow prices are higher than they would be normally. The shadow prices are too high. And Factory K is not motivated to buy resources at that higher price than is dictated by the market equilibrium. And so Factory K would be motivated to find another vendor. So I think the combination of these two non-feasible or suboptimal states, I think they really explain why the dual optimization problem is formulated the way that it is, and it kind of helps to answer the red highlighted and the blue highlighted question from a couple slides ago. The optimal solution must motivate both Factory M to sell and Factory K to buy, and this goes back to how I said it was subjective, that the dual problem is formulated or is presented in Factory M's point of view, because in reality, right, the optimal solution must be optimal for both Factory K and Factory M. So as we get close to the end of this module, I did want to do a side-by-side comparison of primal and dual optimization, which summarizes a lot of what we talked about in this module. So primal optimization is maybe visualized or understood as a resource allocation problem. How can we use our resources, and what should we build from them? What should we generate from them? The dual optimization may be visualized or understood as a resource valuation problem. How much should those resources cost in order to generate the optimum output, the optimum state? The primal optimization is predominantly performed from the point of view of Factory K, whereas the dual optimization, you could say, is primarily from the point of view of Factory M, but as we saw a second ago, it's really from the point of view of both. The objective of the primal optimization is to define the number of each product, X, to be generated such that the income to Factory K is maximized. AKA, we want to maximize the number of the most profitable products generated. And our objective function is equal to C transpose times X, where this is the unit price and this is the number of products generated. The objective of the dual optimization is to define a market price for scarce resources, mu, that maximizes the income to Factory M, or we could say that facilitates the transaction between Factory M and Factory K. The goal is to minimize the market price to maximize the number of resources sold, and the dual Lagrangian, which serves as the objective function for the dual problem, is equal to B sub H, which is the total numbers of the individual resources to be sold times the shadow prices, or the market equilibrium prices for those resources. For the primal optimization, we assume that array C represents the actual price at which the finished products are sold, whereas for the dual optimization, we assume that array C represents the minimum price at which the product Y is sold, although one could interpret the primal problem, or C as related to the primal problem, also representing the minimum unit price at which it's sold. For the primal optimization problem, we assume that customers will purchase all the products from Factory K at that price C, or I guess potentially higher. And for the dual optimization, we assume that Factory K will purchase all the resources from Factory M at that shadow price or market equilibrium price mu. Again, B sub H represents the number of units sold from M to K. Now, a couple bullets here that we're going to use to wrap this up. We observe that both the primal and dual optimization problems, they really share the same objective, the same goal. And we saw that because the primal objective function, which is equal to C transpose times X, is equal to the dual Lagrangian, or the dual objective function, defined as B sub H times mu. They do so by switching the roles of the objective and the constraints, yielding equivalent problems, again for strong duality, that yield the same optimal solution in different ways. And one reminder of that is to look at the slide that we drew from the previous module, where we showed the transform or the conversion from our factory optimization problem. We converted from the primal to the dual representation, showing the actual values in the map. Now this module demonstrates that the shadow prices, mu, are not just a mathematical construct, right? They are values with practical significance in the real world, especially when it comes to discussing problems that have some economic importance. So I wanted to end by presenting a short conclusion of all 8 modules that constitute this series on constrained optimization. We discussed a lot of interesting topics. We provided an introduction to constrained optimization problems, both linear and nonlinear types. We discussed how to use the method of Lagrange multipliers, considering both equality and inequality type constraints, and how we could use the method of Lagrange multipliers to transform the constrained optimization problem into its unconstrained form. We discussed at length duality, the duality principle, and how it may be applied to optimization. It allows us to find the lower, or potentially upper, but really lower bound on the optimal solution to the primal problem. And we focus predominantly on Lagrange duality with a little bit specific focus on linear programming problems. And then the last module, which is the one we just completed, focuses on the economics of optimization with some focus on shadow pricing and the role of duality in economic optimization problem. And we fortunately also included a ton of great MATLAB examples. We used MATLAB to solve a lot of these constrained optimization problems. So that marks the end of this series on constrained optimization. I'm still thinking about what we're going to do next, what the next topic is that we're going to discuss. One of the strong contenders is artificial intelligence or machine learning, but if you have ideas of your own, if there's something you'd like to hear me discuss, a topic you'd like to see me cover, then please throw your ideas into the comment section.